Alright, we're talking about geometric probability today. I'm going to discuss some vocabulary first. The sample space. The sample space is the set of all possible outcomes of an experiment. So if your experiment is flipping a coin, then typically you have heads and tails are the two possible outcomes. So heads and tails would be the sample space. An event is any set of outcomes. So if I say I want to get heads on the coin when I flip it, then that would be the event I'm hoping happens. Or if I want to get tails, that would be the event I'm looking for. But it can be more than one outcome in most situations. So if I'm talking about rolling a die, maybe I say I want to get an odd number. And so there would be 1, 3, and 5. There would be 3 different outcomes in that event. 3 different outcomes that would be odd numbers. The probability of an event is a number between 0 and 1, and this number tells us the likelihood the event will occur. So we're going to be dealing with probability today. If every outcome in the sample space is equally likely, the theoretical probability of an event is, so the theoretical probability is equal to the number of outcomes in the event over the number of outcomes in the sample space. So going back to the coin, the total number of outcomes in the sample space was 2, heads and tails. If I'm hoping to land the coin on tails, there's only one side that has tails, and so I'd have a 1 out of 2 chance. My probability would be 1/2. If I'm rolling the die and I want to get the number 2, well, there are 6 different possible outcomes on the die, numbers 1 through 6, and only one of those sides has the number 2, so I'd have a 1 out of 6 chance of getting the number 2 when I roll that die. So that's how the probability works. Now, so far we've just been talking about regular old probability, but today, I'm jumping the gun here. Let's keep talking about regular probability. An event that is certain to occur has a probability of 1 or 100%. If I'm talking about flipping the coin, I say what's the probability that it'll land on either heads or tails? Then I have 2 events in the sample space, heads and tails, but I also have 2 outcomes in the event, heads and tails. So I'd end up with 2 over 2, which would reduce to 1. If you have a probability of 1, then that event is guaranteed to happen. An event that is certain to not occur has a probability of 0 or 0%. So if
This is security. Can you please go and disarm the school? Once again, this is security. Can you please go ahead and send the opening for the school?
Well, that announcement was a fun addition to the video. Alright. Lost my train of thought now. Alright, so if something is guaranteed not to happen, it's going to have a probability of 0. So if I'm flipping the coin and the only 2 options are heads and tails, and I say what's the probability it's going to land on a blue sky or something, then that's not going to happen. So it's going to have a probability of 0. An event that is equally likely to occur or not occur has a probability of 1/2, 0.5, or 50%. Those are all the exact same thing, just written in a different way. But a lot of times if something is equally likely to occur or not occur, we say it's 50-50. It's got a 50% chance of occurring and a 50% chance of not occurring. So that's a 1/2, a 0.5, or 50%. These are all saying the exact same thing. And the coin, going back to tossing the coin, that is a good example of something that has a probability. You got a 50% chance of landing on heads and a 50% chance of landing on tails. So flipping that coin, you're going to have a 50% chance of that coin landing on heads. Alright, now that we have done that, now let's talk about the main thing we're dealing with today. We're going to be focusing on geometric probability. And in geometric probability is used when an experiment has an infinite number of outcomes. In geometric probability, the probability of an event is based on a ratio of geometric measures such as length or area. The outcomes of an experiment may be points on a segment or in a plane figure. So right now, we're using this for our probability, where you put the number of outcomes in the event over the number of outcomes in the sample space. Well, what happens when those numbers become infinite? Then it makes this kind of challenging to do it like this. So we base it off of a measurement like length or area. So let's try this out on the next page. All right, so example 1. A point is chosen randomly on line segment AD. Find the probability of each event. So we want to find the probability that the point is on line segment CD. So I come over here to line segment CD. The length of line segment CD is 5. So I take the part that satisfies the event. This is what I want to happen. This is where I want the point to land. And I put that over the entire sample space. So now I'm talking about the entire length of the figure. So the length of line segment AD, 4 plus 3 plus 5 is 12. So the length of the whole thing is 12. So I'm putting the length of line segment CD over the length of the whole thing, line segment AD, and that will give me the probability of the point landing on line segment CD. Now, one thing that's not, one thing I forgot to read to you on the previous page was that we want to provide our answers in 3 different forms. One is a fraction, one is a decimal, and one is a percentage. Kind of like we did just a second ago with the 1/2, the 0.5, and the 50%. Because there's 3 different ways to provide probability. I just want to give you practice in doing all 3. So we are going to round our decimals to the nearest hundredth, round our percentages to the nearest whole number. So I'm going to do 5 divided by 12 is approximately 0.42. And as a percentage, that would be 42%. If you don't already know, percent means for each 100. Cent, like century, there's 100 years in a century. There's 100 cents in a dollar. Cent means 100. So when you say percent, you're saying for each 100, per 100. So when I want to go from a decimal to a percentage, I got to multiply it by 100, which moves the decimal 2 places and makes it 42. All right, let's find the probability that the point chosen randomly on line segment AD will be on line segment AC. So I come down here, I want to get the length of line segment AC. To do that, I need to add the 4 and the 3. So the length of line segment AC is 7. Put that over the length of the whole thing again. And the probability would be 7 out of 12. So as a decimal, that would be 0.58. And as a percentage, move the decimal 2 places, be 58%. All right, the probability that the point is on line segment BC or line segment CD. So it can land on this segment or on this segment. Anytime you see that word or, we are adding. Because if it can land on this one or this one, it doesn't need to land on both. It just needs to land on one of them. And so we're just increasing the distance, increasing the length of those segments that are a good possibility for our event. And so I'm going to take the length of line segment BC and the length of line segment CD, and I'm adding those together. And I want to take the length of that of everything in my event and put it on top of the length of the full thing, the sample space basically, which would be 12. Number of events in the sample space. In this case, it's actually the length of the sample space. So 8 divided by 12 reduces down to 2/3. We haven't had to reduce the past couple of fractions, but we always want to reduce a fraction if we can. So 2/3. As a decimal, that would be 0.67 if we're rounding to the nearest hundredth. And as a percentage, move the decimal 2 places. It would be 67%. So there's our answer as a fraction, decimal, and percentage. All right, last one on this example. Again, we're doing OR, so we're going to add. Line segment AB is 4. Line segment CD is 5. 4 plus 5 is 9. I put that over the length of the whole thing. And then we want to reduce. 9 over 12 reduces to 3/4. As a decimal, that is 0.75. Move the decimal 2 places, and the percentage is 75%. All right, let's look at example 2. All right, use the spinner to find the probability of each event. Okay, so we're going to spin this spinner and we want to see where it's going to land. Well, hopefully we can just look at this and we can see you're going to have a better chance of landing on yellow than you will on green, because yellow is a much bigger space. It's taking up a higher percentage of the circle, so it's got a higher percentage probability of being landed on. Okay, so whatever percentage of the circle something's taken up, that's going to be the probability that it's going to be landed on. So we, again, just like the last one, we're kind of putting the part over the whole with these measurements, and we're focusing on the number of degrees in each one of these sections. If you remember, a circle has a total of 360 degrees. So if I want to know the probability that the pointer will land on red, I'm going to take the number of degrees from the red section, that part, and I'm going to put over the whole thing. There's 360 degrees in the whole circle. So there is the probability. I always want to reduce if I can reduce. And that will reduce to 2/9. We're going to give it as a decimal, which will come out to 0.22. And again, move it 2 places, move the decimal 2 places to get percentage. Be 22%. So there's our probability for landing on red. That red sector is taking up 22% of the circle. So if we were to spin this spinner, you're going to get a 22% chance of landing on that red section. Okay, what about the probability that the pointer will land on green or blue? Remember when we see that word or, we're going to add, right? So green was 45, blue is 60. Those are going to add up to 105. So we got 105 degrees out of the total, which is 360 degrees. So 105 divided by 360 reduces to 7 over 24. As a decimal, it rounds to 0.29. So as a percentage, that will be 29%. All right. And then we want the probability that the pointer will not land on yellow. Not land on yellow. So basically, anything but yellow is good. So the way I want to do that, I know that the entire circle is 360 degrees. Yellow is 100 degrees. I'm going to subtract the 100 from 360, and that'll tell me what's left outside of yellow. This is the number of degrees that everything except for yellow adds up to. You could also just add these together if you want. And that'll give us the number of degrees that is not yellow. So 260 degrees over the 360, the whole thing. And we want to reduce the fraction. And it reduces down to 13 over 18. If we get that as a decimal, it will round to 0.72. And again, we move the decimal 2 places for percentage. Should be 72%. So 72% of the circle is not yellow, so you got a 72% chance of landing on something that is not yellow when you spin the spinner. All right, let's look at example 3. All right, find the probability that a point chosen randomly inside the rectangle is in the shaded region. So we're dealing with a two-dimensional figure here, so it doesn't say the word area, we're dealing with area here. Notice these are all square units, and that's what area is. It's a number of square units. So one thing I could do is I could count how many squares there are, and then I could count how many shaded squares there are, and I could use those numbers for my probability. But we have learned that there are some formulas we can use. So for this, I want to do length times width, so I'm just going to count how far the length and width are. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is actually a square. You can either do length times width, or you can do side squared. But however you do it, whether it's 10 times 10 or 10 squared, you're really doing the same thing. You should find out that the area of this entire square is 100 units squared. Now I want the probability that I'm going to, that a point chosen randomly would be on a shaded region. I need to find out how many of these square units are shaded. So I already counted this was 10. Looks like there's 2 less over here. So that'd be 8. So 10 plus 8 is 18. There's 2 less again. So 18 plus 6 is 24. 28, 30. So there are 30 shaded square units. Okay, so I'm going to take the part that satisfies the event I want to happen. I want to get a point in the shaded region. There are 30 shaded boxes over a total of 100 boxes. So I put the 30 over 100 and we reduce. And that reduces down to 3/10, which as a decimal would be 0.3. And if I move the decimal 2 places, be careful here, it's going to move 2 places, I'll end up with 30%. So 30% of the area is shaded. So if I chose a point randomly in that figure, I have a 30% chance of landing on the shaded region. All right, so we're going to use the same concept down here. I'm going to get the area of the whole thing. It says find the probability that a point chosen randomly inside the rectangle is in the shaded region. I need the area of this entire rectangle. And then I need to know the area of the shaded region so I can put the shaded area on top of the total area. So first, this whole thing is a rectangle, so I want to do length times width. So the length is 16, the width is 12. So I'm just multiplying 16 times 12 for the area of the rectangle. All right, so the total area is 192. So then I need the area of the shaded region. Well, what shape is that? If you notice, all these right triangles here are congruent. Each right triangle has legs of 6 and 8. I could do Pythagorean theorem to find this piece, and if I did, I would find out it was 10. This is going to give me the exact same thing. This is going to give me the exact same thing. So what I find out is all these sides are congruent. Now, I can know specifically that they're 10, but the important part is that they're all congruent to each other, which means that this shaded shape right here is a rhombus. So the way I can find area of a rhombus is 1/2 times diagonal 1 times diagonal 2. So what are the lengths of the diagonals? Well, if I look at this diagonal, the length of that diagonal should be 12. The length of that diagonal is 12. And what about the length of this diagonal? This diagonal should have a length of 16. So when I do 1/2 times diagonal 1 times diagonal 2, we find out the area of that shaded rhombus is 96 square units. So I'm taking the shaded area, putting it on top of the total area, and that will give me the probability. And that reduces down to 1/2, which is equal to 0.5, which if I move the decimal 2 places, is the same as 50%. And you can notice, first off, the 12 and 16 are getting multiplied in both of these. The only difference in the formulas is this one's getting multiplied by half, so it's going to be exactly half the size of this one. And also, if you kind of look over here, when I drew those diagonals in, it split this picture up into 4 smaller rectangles, and in each one of those rectangles, it split half and half into shaded and unshaded. Each one of these rectangles is half shaded and half unshaded. So exactly half of that rectangle is shaded in. So if we pick a point at random in that rectangle, half the time we're going to get it in the shaded region, and half the time it'll be in the unshaded region. All right. So far we've just been dealing with one event happening. Now we're going to talk about 2 events, but we're going to focus on independent events. So 2 events are independent when the occurrence of one event does not affect the occurrence of the other event. So if I have 2 coins and I'm going to flip them, whatever I get when I flip the first coin has absolutely no effect on what I'm going to get when I flip the second coin. So flipping those 2 coins would be independent events. One does not affect the other. All right, if 2 events are independent events, the probability that both events will occur is the product of the probabilities of the events. So this is how we express this same concept in letters and symbols. This is the probability of event A and event B happening. The probability of both of these happening is the probability of event A times the probability of event B, because that's what product is. It's the result of multiplication. So if I find the individual events' probabilities, I can multiply them to get their product, and that will give me the probability that both events are going to happen. So let's test this out. 2 points are chosen randomly on line segment AD. Now this is the same picture we used earlier. The length of the whole thing is 12. What is the probability that the first point is on line segment AB and the second point is on line segment CD? So what we're going to do is just find the probability of each individual event first. So line segment AB is 4 units out of the total of 12. Now you can reduce these if you like, but it's not completely necessary because we're going to multiply them in a second. So we could just get our reducing done at the end. The second point is on line segment CD. Line segment CD is 5 over the whole thing of 12. So here's the probability I get a point on line segment AB. Here's the probability I get a point on line segment CD. If I want to know the probability that both of them are going to happen, I need to multiply. And when I multiply them, I get 5 over 36. So this is the probability that both events are going to happen. And I want to write that as a decimal, so it rounds to 0.14, and move the decimal 2 places will give that to us as a percentage. Alright, what is the probability that the first point is on line segment AC? Line segment AC has a length of 7. And the second point is on line segment CD. Line segment CD has a length of 5. So again, I've gotten the probabilities of the 2 individual events happening, and then I just have to multiply them to find the probability that both will occur. So we find the probability is 35 over 144. As a decimal, that would be approximately 0.24 and approximately 24%. Alright, let's look at our last example. The spinner is spun twice. What is the probability that the pointer will land on red for the first spin and land on yellow for the second spin? So, probability of landing on red, 80 over 360, because remember there are 360 degrees in the full circle. Probability for landing on yellow, 100. So 100 out of 360. So there are the probabilities of the 2 individual events happening. So I just multiply those, and it'll tell me, the calculator will tell me what the probability of both events occurring will be. So when I multiply those, come up with 5 out of 81, which when I round to the nearest hundredth as a decimal is 0.06, which as a percentage would be 6%. So I only have a 6% chance of spinning it and getting red, and spinning it a second time and getting yellow. Alright, last one. What is the probability that the pointer will land on green for the first spin? Green, 45 out of 360. And not land on blue for the second spin. Alright, well blue is 60 degrees. So if I'm doing not blue, it can be anything but the blue section. So I'm going to take the total of 360, subtract what's blue, and that'll tell me everything that is not blue. So not blue is 300 degrees out of 360. So here are the probabilities of landing on green and landing on something that is not blue. And I just need to multiply them to find out what the probability of both of them happening is. And when I multiply those, you get 5 over 48, which rounded to the nearest hundredth as a decimal is 0.10. Which is approximately 10%. So I got a 10% chance of spinning green and then spinning something not blue.